I am very impressed with the people of Ecuador. It is the first time that I have known anyone to choose voluntarily to leave the oil in the ground in order to protect the people and the land and the planet. Well done. I am honored to be with you, in part because I come from the colonizing culture, and I thank you for the opportunity to share what I do know. My background is in strategic planning and economics in the oil and gas industry. And when I started working in Texas 30 years ago, there was no discussion about decommissioning. And still today, we do little decommissioning in the state, but we have hundreds of thousands of wells that need to be both plugged in the wellbore below ground and removed and remediated at the surface. My home in Texas has not yet come to grips with the issue of paying for the end of life. I have not worked, I do not know the oil fields in Ecuador in as much detail as Dr. Reyes, but I will explain to you important dynamics at a large scale that you need to plan for and think about in order to accomplish the objective. Can you show the slides in Spanish? On Espanol, please do not try to read my slides. You can read them later. I will say the things that are most important. This first slide number one, numero uno. This first slide shows the natural life cycle of an oil field. An oil field is not like a factory. We do not build the factory or build the oil field, produce it at a constant volume until the end of life. Instead, a well begins producing at the highest rate it will ever produce. It is all downhill, lower and lower rates after initial production. In the early part of the life of a field, we are drilling more and more wells, so the total production increases even though individual wells are decreasing. Perfecto. Muchas gracias. The very first part of the life cycle is to explore and find the field. There is nothing to produce until we find a new accumulation. Then we go through the process we call delineation, which is to find the edges. How big is this new thing we discovered under the ground? Then we go through the process of drilling more and more wells until we have enough wells to get the oil we believe that we can get. After we're finished developing, then the field as a whole begins to decline. Sometimes a field will go through a second stage of development. Someone will bring a new idea, a new process, and you can temporarily improve production. But it is a finite resource. It is eventually drained. Production does stop. This last phase of life is abandonment, closure. You'll notice that I have shown the lines bend down. That is because the life of the field depends upon a minimum level of production. A single well could continuously decline, but the group of wells share facilities, and when the group of wells ceases to be economic, then all of the wells cease to be economic. Now, this graph shows how the economics work. It pertains to a single field offshore, so we do not see the ramp up in development. But this is an example cash flow that comes from a standard document to describe how to evaluate the volume and the economics at this blue point in time. Each bar represents 1 year, and the height of the ball money going out in the form of capital investment or coming in as profit. So the document describes how to evaluate an initial investment, where we see significant capital investment going out. When it starts producing, we get very significant profit coming in, but it declines systematically until the end of life when we pay for decommissioning. If I, and in my training and in my experience, that is where the oil industry evaluates economics most. We use the same tools, the same economic tools, to evaluate a property in the middle of life. The problem is that those tools do not work very well. At this point in time, this example makes $600,000 a month. It will survive and make money for 13 years, and the net present value is $25 million. It looks like, by our traditional, normal economic tools, that this is still a profitable field. However, at that point in time, the total future cash flow is zero. It will cost $37 million to plug the well here, and all of this 13 years of cash flow equals $37 million. If you pay $25 million to buy it, you earn $37 million, you pay $37 million, and at the end of the day, you have lost $25 million. It is a long time when a large part of the life, an oil field, is financially upside down. It owes more than it will make. This concept I call holdback. I created that idea to explain the economics. The oil industry is still learning that that is true. Now let's look at Block 43. This graph shows the production history in green on a scale of 0 to 100,000 barrels a day. Each of the 3 lines made up of points represent different forecasts that have been published by Petroecuador in the last few years. The peak production was 83,000 barrels a day, and to the extent I make a mistake, I am wrong. I trust Dr. Reyes to correct me. The company spent about $2 million to achieve that. There was some additional development in 2023 and 2024. As it stands today, the most recent production is still about 43,000 barrels of oil per day. But all 3 of the block has produced roughly 180 million barrels of oil. These three forecasts that were created in the last few years all predict a rapid decline. When, due to the nature of the reservoirs, when the company stops performing work to manage and improve production, it will quickly decline on the order of 25 or 20 to 50% per year. Very rapid. At this point in time, as of today, about 90% of the oil that is predicted in the simple case to be recovered has already been produced. Approximately, and I'm interpreting multiple sources of data that are not well defined, approximately 25 million barrels would be produced through 2035 if it went on natural decline. And it has produced 180. So the first 10 years created 90% of the cumulative production. The last 10 years, the 10% of production, which means that the money necessary to pay for decommissioning is largely in the past, if the money comes from the same field. In 2023, PetroAmazonas estimated the cost would be $500 million, but the more recent estimate is $1.3 billion. Cost estimates, like reserve estimates, volumes of reserves, are both uncertain, and a single number cannot be understood unless you also understand the associated uncertainty. When I say that 25 million barrels remain in the natural decline scenario, makes assumptions about what would be done. And when I say the cost is 1.3 billion, it has an uncertainty range associated with it. It is technically called a class 5 estimate. It means a very wide uncertainty. It could be 50% less, or it could be 100% more. So these two estimates are not entirely at odds. But for our discussion, we will use the $1.3 billion. $1.3 billion is a lot of money by comparison to anything, by comparison to the $2 billion spent to initially develop the fields. Now, the good news is much of that work will be spent within the local economy. In Texas, one of the biggest reasons, and in the United States, one of the most compelling arguments to do the decommissioning work is employment for oil field workers and the local economies. Whether that applies here or not, I do not know. The natural, obvious, ethical solution is for the oil company to pay that cost of decommissioning. And what decommissioning has occurred in the world to date has happened because oil companies have taken money from younger fields with higher cash flow and used it to pay for the old fields at the end of their life. But oil companies do not save in advance. That is not part of the business model. An oil company is driven by net present value, which is a measure of economic success. decommissioning a well has no financial return. It is literally, from their perspective, literally the same as burying your money underground. No returns, no interest, no planning. To the extent that it has been paid, it comes from other successful fields. And that is still the case today in Petroecuador. There are many other fields producing and making a profit whose cash flow could be used to pay for decommissioning here. Companies could save in advance. In fact, they do not. And in the United States, when companies have been pushed to realize that they are in a bad financial position, the argument usually is they usually argue that they should be allowed to drill more so that they can make more money so that then they can pay for decommissioning. But the same problem exists. The same decommissioning cost will come due. The more you drill, the more the cost is going to be. Also, there is always risk and uncertainty that the plan to drill more may not work. You might make a bigger problem in the process. But that is the thought process of the companies. So to the extent that companies cannot or do not pay their obligations, instead they may go bankrupt. We have a long history in the United States of companies going bankrupt and leaving their wells unplugged, leaving messes behind. In that case, we have programs from the government to pay for that decommissioning. Now, the scale of orphaning, we call it, because the person responsible is no longer responsible, the government becomes responsible, so we call that orphan. There have been programs for a long time, and they are growing because it is in the public interest for the wells to be plugged. So if the company does not do it, or the industry does not do it, then the public will do it with taxpayers. Or there's only one other alternative, and that is the work is not done. There are only two classes of finance at this scale. It will be the public, or it will be the industry, or it will not be done. Now, Adam understands how to optimize costs and improve local impact. And another speaker, Brad Handler, will discuss options of international finance that could help either one of these. But those are structurally the three basic options. But this issue of paying for the decommissioning applies not only to Yasuni, not only to Block 43. This is the second scientific concept I want to explain to you. It's called the Hubert curve. Theory says that in a basin or a country, production of oil as a whole should increase to a peak and decline at approximately the same rate. Now, this graph shows the Hubert curves of the United States. I've broken it into three parts. The main part is the green, and the scale is very large. This is 100 years. The highest production in the United States was 1971, until we discovered a new class of resources in the subsurface, and that's the shale revolution. The about 90% of the wells in the United States pertain to this dark green curve. We have one set of wells that are highly productive and a much, much larger set of wells that are not very productive at all. They represent most costs. This graph shows national production from 3 countries in South America. Colombia does have a dip. The Hubert curve can be disrupted by large-scale political or economic factors, but still a relatively symmetrical curve, and in Argentina, a peak and a curve. This increase is the Vaca Muerta shale, where they have also started new production. Most importantly, the dark blue line is Ecuador. Now, my research shows 2 paradoxical bits of information. The pace of drilling in the last 10 years is only about a third of what it had been, but maintaining production has required a great deal more investment. So in order to hold the production relatively flat and to cause it to decline only a little bit required $1 billion worth of investment in 2024. Looking forward, though, Ecuador has no shale resources. Exploration has been less successful and finding smaller fields. In theory, it might be possible to redevelop the existing fields to improve recovery, but that will involve a large number of wells, a lot of activity, and a lot of money. Ecuador is probably already in permanent decline. Its production is probably in permanent decline, which means it is time to begin planning for decommissioning of the oil industry as a whole. This table on the left shows the various estimates of decommissioning costs for the 260 wells approximately in Block 43, according to the documents that made the estimates. As I understand it, there are about 5,400 wells in the country, and about half of those are already standing idle permanently, which is to say about half of the wells in the country are no longer creating cash flow. They are a pure liability. It is not very accurate to extrapolate the cost estimates from Block 43 to the entire country. First, because they are estimates. No one has decommissioned an entire field in Ecuador before. Second, because the costs are only partly related to the wells themselves. Costs also depend on the facilities. For discussion purposes, it is still valuable to consider extrapolating the costs. And it looks like this. The cost of decommissioning the oil industry in the Amazon today, if it were all paid today, would range between $14 billion and $56 billion. If half of those wells could be decommissioned now, then the liability presently, right now, is approximately $13 billion, which is 6 times the cost of Yasuní, Block 43 alone. So the Petroecuador and the country as a whole must face the same question. Will the money come from producing other fields? Will it come from redeveloping the same fields, or will it come from the taxpayers? there are two systematic, large-scale risks that the country must consider as it plans for those options. This graph shows the national production in the top line and the two major pipelines that constitute the large majority of the national production. I have zoomed in to a closer detail to show you two dynamics. This second line represents the SOTA pipeline, and it is declining about 4 or 5% per year. Its throughput is, but it is still operating at about 73% of capacity. The risk with this pipeline is primarily the fact that it is 50 years old. And in the last 5 years, there have been 7 major disruptions. The second pipeline has a larger capacity, but a lower throughput. The OCP pipeline has been declining even as Block 43 has continued to produce. When Block 43 stops production, the throughput of OCP will be approximately 33%, which is beginning to approach the minimum throughput capacity to operate the pipeline. I do not know exactly what that minimum is, and it might be possible to reroute oil from one pipeline to the other. If it is not possible to combine the pipelines, then Petroecuador should expect sometime in the near future not to be able to sell approximately 100,000 barrels of oil per day. The facilities require the pipeline requires a minimum throughput capacity. When that is reached, pipeline will quit operating. Now, there are engineering answers, and we may be able to reroute, we may be able to redesign the pipelines, but this requires explicit planning. Now, back up at a large scale again, this graph shows the national production of oil and the national consumption of oil. Production has been declining for 10 years, probably will continue to decline. Now, there is a risk that production will decline much more rapidly in the future than it has in the recent past. But these two curves are more important to real life. This curve is the gross export, and this curve is the net export. Already, those have been declining much more quickly than production because it is getting pinched. The money that Ecuador makes from exports is being pinched as production comes down and use goes up. The net export rather has decreased by about 1/3 already. Now let's look forward. This is a rough extrapolation. It shows what might happen if the trends do not change. Ecuador began importing refined products around 2005. If Ecuador continues to use oil and increases consumption like this, then within 5, 10, 15 years, production will decline so much that Ecuador will import more than it exports. On a on a volume basis. But the crude that gets exported is much less valuable than the refined products that are imported. The consequence is that the oil industry in Ecuador will stop being a credit to the national account. It will become a debit to the national account much earlier. The country's participation in the oil industry will become a liability that causes you to pay more money to the external world than you make from the external world. And that will happen within the planning horizon. It is a very hard problem because you're not just for the sake of the energy transition and causing less harm to the planet, but also for the sake of managing your national economy and the price of gasoline and diesel. You need, the best option is to decrease your use, but that requires a use of petroleum. That requires managing an increase in demand with a decrease in production and income, together with the natural decline and the decommissioning costs that come due. It is a hard problem. I am so glad you are here to try to solve it together.